All right, welcome back everyone. And we're going to go ahead and continue the discussion we have about the analysis and design of the bandpass filter based on transmission line and coupling gaps. So where we left things off is that we have been able right now to derive essentially our circuit, which is shown here with the J inverters and the resonators. So these are the resonators, obviously. We have chosen here to work with shunt resonators. Of course, we could have worked with series ones. But as we discussed before, the challenge is that all the equations we have derived so far are essentially linking these J inverters with the actual capacitance values and actual inductance values. So that's useful if you're going to make the circuit out of real LNCs. But if you're going to make the circuit with some other type of a resonator, and in this particular time, we're talking about transmission line resonators, then there is no explicit way to link that. And so the challenge right now and the next step in the design process is to solve exactly that problem. So the way we solve this problem is by actually considering the resonator's acceptance, the one I'm showing here as B. So in fact, it's slightly more convenient, instead of considering this acceptance, is to actually consider the normalized derivative at resonance. So for every single resonator that you can actually design, you can essentially compute this number here, or simulate it or measure it, and then essentially for every resonator, you can essentially compute this little b. For example, for the the lumped element resonators that you see right here, that b is actually given right here, and of course, considering that LC is equal to 1 over omega naught square, essentially, the B has very simple expression, is either the capacitance times the omega naught or 1 over inductance times omega naught. That's the case for the lumped element. But again, for every resonator, no matter how complex it may be, there's going to be an expression that links that B with C prime or L prime. And so that essentially means I can go ahead and use my original equations and actually replace that C or L that I had in them with the new B's that I just derived. For example, the very first one is going to basically have the equation right here, where you can see I have replaced essentially my capacitance with B1. As a reminder, this is the fractional bandwidth, meaning the absolute bandwidth divided by my center frequency. And something very similar will be true for all resonators. So this is an all inverters. So this is essentially the last inverter, and this is basically the inter-resonator inverter. So clearly the advantage of this description compared to the original one is the fact that this description now is applicable to any resonator type, not just the lumped element one. Now let's talk about the second part of the design process, which is dealing with our explicit transmission line equations. As we discussed before, the main idea here is that we're considering open transmission line sections, and we're going to use them in their second resonance, meaning where the electrical length is about 180 degrees. So essentially, we're dealing with open resonators that are about half a wavelength. And the reason for that, as has been discussed before, is because the equivalent circuit now for each one of these just around resonance is basically an LC. Now, if you take the equations we have actually derived for this open resonator and you calculate the B, the susceptance of this resonator, is nothing else but Y naught tangent theta. And just around resonance, you can approximate this with a linear equation, which is simply Y naught, the characteristic admittance of the resonator, times theta minus pi. So that means now you can compute this B that we always wanted. So you differentiate the susceptance with regards to frequency. The math is pretty simple, and that little b is nothing else but Y naught pi by 2. So we're basically now ready to go. I can compute every single admittance, every single inter-resonator coupling, and every single inverter. So I plug in the equations here, and I'm going to make the assumption here that my input admittance GA is equal to Y naught. And so here's the equation for the first coupling, the coupling between the source and the first resonator, which, by the way, later on we're going to call it external coupling. Here's the equation for the inter-resonator couplings. That will be true for all the couplings from the beginning until the end. And here's the last external coupling, the coupling between the last resonator, this guy right here, and essentially my load, which is right here. So now I have all the equations ready. Essentially, once I know my G's, which of course I will know because I know what filter I'm trying to design, for this particular example, I can immediately calculate J's, and then that brings us to the last step, which is linking these J's to these gaps. Remember that those J's will be needed to compute the gaps between the resonators.